We spent a while on ray tracing, and then we got to the lens equation. Now I want to do some examples with the lens equation. So this is a video about lens equation examples. For the first one, I would like to do a convex lens. Let's have a focal length of 20 centimeters. Now, when we talk about a lens having a focal length or a mirror having a focal length, you can pretty much always assume that you are being given the absolute value of the focal length. You're going to have to decide on the sign based on the sign conventions. We are going to put our object, we're going to say is 10 centimeters from the lens. And we need to recognize that that's our D object. I would like to find D image, maybe the height of the image, the magnification. Let's have an object height. Of 12 centimeters. So if I've got this, I can draw it out, and I actually probably would, just to be able to get a sense of what's going on. If this were a multiple choice question I were facing on a standardized test, I would definitely do this. I'd say here's maybe 20 centimeters, here's 10, that's half the distance, here's 10, here's 20. If I've got my object at 10 centimeters, I would expect that I'm going to get, something like, here is one ray that's parallel, and then through F. Here's a ray that goes through F prime and is then parallel. So I know that I'm looking at something back here. I'm looking at something back here. I am expecting a virtual image, a virtual upright enlarged image, which might be enough on a standardized test to get me to an answer. It could be that I need a little bit more. I'm going to say that this is a magnification of, I don't know, maybe that's something like double. Magnification is going to be a positive number, positive, maybe 2, ballpark. I mean, I just sketched this real quickly. I didn't measure anything. I'm flying pretty fast and loose. But let's see what we've got. Using my lens equation, 1 over DO plus 1 over DI equals 1 over F. Virtual image means I'm expecting DI to be negative. I'm expecting HI to be positive. Magnification, magnitude is going to be bigger than 1. So I'm solving for DI. I'm going to say 1 over DI equals 1 over F minus 1 over DO. 1 over F, that looks like 1 over 20 centimeters minus 1 over DO, which is 10 centimeters. 1/10 is bigger than 1/20, so I am getting a negative. 1 over 20 minus this thing I can write as 2 over 20. Gives me a negative 1 over 20 for 1 over DI. So my DI is going to be negative 20 centimeters. I knew my F was a positive number. That was the big thing I needed here. I said F is positive for a convex lens. So I get a DI of negative 20 centimeters. My magnification equals negative DI over DO is negative negative 20 centimeters over 10 centimeters is positive 2.0. Hey, that was a pretty good guess. Is positive 2.0, and that means that my HI is going to be my magnification times my HO is 2.0 times my 12 centimeter height equals 24 centimeters. And then I was looking for magnification. I've got that. So that's it. I've got a virtual upright image, positive height, positive magnification. It's enlarged. It's over here on the left. Now I want to do another. Let's try a concave lens. So a concave lens. And I would like to do a focal length of 20 centimeters, which is actually the focal length that you see more often than anything else. I'm not sure why. And let's have our object distance be 40 centimeters and see what this does. There's my lens. I like to draw the picture anyway because I think it can be a helpful thing to just get a basic idea of what sorts of numbers to expect. So maybe 20 centimeters, 40 centimeters, that looks like twice as far. 20, 40, I'm ballparking these numbers. For a concave lens, I know that my focal length is a negative number. So this one is f over here, this one is f prime over here. If I'm putting my object out at 40, and I just quick ray trace this thing, I'm going to go once through F, or once parallel, and then through F, and then I'm going to go once through F prime, and then parallel. Those outgoing rays, they're not going to do anything, so I've got to trace these things back. It looks like I'm going to meet here. I'm going to end up with an upright virtual image. So I expect upright virtual reduced, or upright I expect, let's give this thing a height again. Let's say our object height is 12 centimeters. I'm doing 12 because it divides 3 and 4 and 2. It's helpful. Upright tells me that I'm going to have an HI that is positive. Virtual tells me I'm going to have a DI that's negative. Reduced tells me I'm going to have a magnification magnitude less than 1. Let's try it. 1 over d object plus 1 over d image equals 1 over f. 1 over d image equals 1 over f minus 1 over do equals 1 over f. 20 centimeter focal length, but concave lens, so it's negative, so negative 20 centimeters minus 1 over object distance is 40 centimeters. This is 2 over 40 negative minus 1 over 40 makes 3 over 40 negative. And that is 1 over di. So my di must be negative 40 over 3 centimeters, or negative 13.3 centimeters. I do get a negative di, which is what I expected. Now let's see, my magnification is negative di over do is negative 13.3 over 40. The negative and negative cancel. This is 40 over 3 divided by 40, which is 1/3. So I'm going to get a magnification of 1/3. positive 1/3. I do get a magnification that's reduced. I get an image height. My image height is the magnification times my object height. So I'm going to get 1/3 times 12 centimeters equals 4 centimeters for my image height. That's positive. Everything checks out. And I'd like to do one more. Last one, I want to do a concave mirror. I would like to have a focal length of 15 centimeters. Let's have an object distance of 20 centimeters. And we'll keep our object height at 12 centimeters and see what's going on. A concave mirror looks like this. No. Looks like this maybe. My light rays are bouncing together in this location, so my F is going to be a positive number. That's what I need out of this. If I were to just try to quick sketch it and do my ray tracing business and see that this side is silvered, I said in focal length of 15 centimeters. Let's go 1, 2, 3 dots, 15. Object distance 20 centimeters, 4 dots, 20. There's a height. I'm going to have a ray that goes parallel to my axis and then through the focal point. I'm going to have a ray that goes through my focal point and then parallel. It looks like these are going to meet over here, so I expect inverted, meaning HI is negative. I expect real, meaning DI is positive, and I expect enlarged, meaning magnitude M is bigger than 1. That's what I get from my quick version of ray tracing. This like 1.5. This is 4. I don't know. Might be an M of 3-ish. Negative 3. Let's try that. M of maybe negative 3. Bigger than 1 and negative. 1 over D object plus 1 over D image equals 1 over F, 1 over D image equals 1 over F minus 1 over DO. Let's plug in some numbers. 1 over, it's a positive focal length, so 1 over 15 centimeters minus 1 over 20 centimeters. Common denominator is 60. So this is 4 over 60 minus 3 over 60 is 1 over 60. So my DI is going to be a positive 60 centimeters. And let's see what that does. I'm going to get a magnification. So there's that one. Magnification is negative DI over DO. DO is a negative 60 over DO, which was 20 centimeters, is negative 3. And then we'll keep running with this. My image height is going to be magnification times my object height is going to be negative 3 times 12 centimeters. My image height is going to be negative 36 centimeters. I got a negative height positive image distance magnification. This way, I guessed from a quick ray tracing a magnification of about -3, and I got it. So I'm not doing anything particularly fancy with this. My ray tracing is helpful, and I spent a long time developing that idea. It's helpful even when I don't carefully measure my stuff out. It gives me a range of what I can expect. It's faster than doing the math, right? Like this math, that takes a minute. It's not a huge amount of time, but it's something. That took a minute. This took a minute. If I'm doing a multiple choice test and I'm given this kind of a situation where I've got a concave mirror and here's my focal length, here's my distance, and whatever, and I'm given some answer choices for like magnification is -3, magnification is -1/3, magnification is +1/3, magnification is +3. I can look at something like this. I know 3 is going to be involved, and great, but from this really quick sketch, I know it's negative right away, so now I'm down to a 50-50 guess. I wouldn't maybe be able to tell you that that's going to be a scale factor of 3, but I can tell you it's more than 1. I can do this without having to do any of this math at all. So it is a helpful thing to have that ray tracing in your back pocket, but being able to do the math, that's good too.